Examine the key equations that govern projectile motion. For horizontal position, we use x equals x naught plus v naught x times t. The horizontal position changes at a constant rate. For vertical position, we have y equals y naught plus v naught y times t minus 1/2 gt squared. This accounts for gravity's constant acceleration. The horizontal velocity remains constant throughout the motion. It equals the initial horizontal velocity. The vertical velocity decreases linearly with time due to gravity, following Vy equals v naught y minus g times t. These equations completely describe the motion of a projectile under constant gravitational acceleration. Now let's examine how to calculate important values for projectile motion. The trajectory of a projectile is a parabola. We can derive useful equations to find key points along this path. The maximum height is reached when the vertical velocity equals 0. At this point, the object momentarily stops moving upward before falling. The time of flight is the total time the projectile is in the air. For a projectile launched from and landing at the same height, it's twice the time to reach maximum height. The range is the horizontal distance traveled. For a projectile launched from and landing at the same height, it depends on the initial velocity and launch angle. Let's work through a practical example. We want to calculate the landing position of a ball thrown at 45 degrees with an initial velocity of 10 meters per second. Step 1. Find the components of the initial velocity using trigonometry. The horizontal component equals the initial velocity times cosine of 45 degrees, which is 7.07 meters per second. The vertical component equals the initial velocity times sine of 45 degrees, which is also 7.07 meters per second. Step 2. Calculate the time of flight using our equation. The time of flight is 2 times the initial vertical velocity divided by gravity, which equals 1.44 seconds. Step 3. Calculate the range, which is the horizontal distance traveled. The range equals the horizontal velocity component times the time of flight, which is 10.2 meters. Let's visualize the complete motion of the projectile from launch to landing. Projectile motion principles have many practical applications across different fields. In sports, understanding trajectories helps optimize the performance of balls, darts, and other projectiles to achieve maximum distance or accuracy. In engineering, these equations are used to design water fountains, catapults, and various projectile delivery systems. In physics education, projectile motion demonstrates fundamental principles of motion, gravity, and even air resistance effects.